Hello and welcome to a new session for this online course on Introduction to Embedded System Design. I am your instructor Dhananjay Gadre. In this session, we are going to consider remaining topics related to analog and digital converter and the ability of the microcontroller to read and generate analog voltages. We are also going to consider how the microcontroller can generate random numbers and a little bit part about one of the experiments that you previously saw that we did, which was to power a MSP430 microcontroller using a Lemon battery invoking the low power modes. I am going to show you little more details about it. So, in this lecture we are going to talk about first of all the random number generators. Now, random numbers are very important for embedded applications. A random number generator produces a random number which cannot be reasonably predicted apart from being by a random chance. These can be true hardware based random number generators, although there are no true random number generators. All mechanisms are some sort of pseudo random number generators. You can do that using a hardware approach or you can utilize some software approach. We are going to discuss both these methods here. Now, what are the applications of such random number generators? You would use it in computer simulations. You can also use it for gambling. You may have seen that one of the projects that we demonstrated in the second lecture was dice, and for that we use some sort of random number generator. You could use it in cryptography and many security applications, and there are many such applications. Now, what are the various methods by which you can generate such random numbers? One is using a noise, because now noise is random. So, if you sample that noise, you would get a value which is random, and therefore, this could be a source of your random number. You could use for that noise source, you could use a high value resistor, you could sample external sound and so on. Another source of such hardware noise is through a Zener diode. You could use a switch to stop a high frequency counter. The value in that could be random. If the switch press is an asynchronous event, that is, a human has pressed it. You can use interesting topology called a linear feedback shift register. We are going to dedicate few slides on describing what a linear feedback shift register is. We are going to show a couple of experiments how we can use Lfsr to generate pseudo random numbers, and at the end you can also use built in random function that many embedded C compilers support. Now, a linear feedback shift register is a shift register. Basically, it is a whole few D type flip flops, which the output of one feeds the input of the second and so on, and then the last one is fed back into the input. Of course, you just do not connect it like that, you operate on the outputs in some way, and the linear function could be through a XOR or a XNOR gate. Now, because these are flip flops, you need to initialize them with some value when you turn the power on, and that value is called the seed value. The linear feedback shift registers work on the principle that if you have n bits of flip flop, then if you choose these feedback function appropriately, you could have in principle 2 raised to power n minus 1 combinations. So, this is just like a counter. When you have a n bits of D type flip flops, you can generate 2 raised to power n combinations, except in a counter these are always you know either it is increasing value or decreasing value, up counter or down counter. So, you have 2 raised to power n. In the case of Lfsr, what is called as a maximal length Lfsr, you will not get 2 raised to power n combinations, but 1 less, and that is why we say it is 2 raised to power n minus 1. We will see why it is so. Now, basically Lfsr consists of D type flip flops, as you see here. Here is the input of the first one that feeds the second one and so on. Now, from some of these flip flops you take the output and pass it through certain XOR gates, and that feeds the input. Now, when you load it with the initial number and then you apply the clock, for every clock signal the values that the flip flops will produce, they will appear random, and that is why this is called a pseudo random number generator. Now, the combination, in this case we have shown a 8-bit LFSR. Now, wherever you take the value out, here, here, here and here, these are called taps. So, we have taps at 8, 6, 5 and 4 for a 8-bit shift register. Now, how do we find out where these taps should be applied when you have a different length of LFSR? Well, you do not have to sweat too much. If you search the internet, you will find many sources. For example, we have taken this source from a Xilinx website, and they have a linear feedback shift register, which instead of using XOR gate, it uses XNOR, and it has the value of n, that is the number of flip flops from 3 to 160 bits. And you can imagine the total number of random sequences that will produce is 2 raised to power 161 minus 1, and that is a very, very large number. Remember that 2 raised to power 20 is approximately a million, 2 raised to power 30 is a billion, and so you can imagine what 2 raised to power 60 would be, a very, very large number. So, the sequences that such a shift register will produce, compared to the last value, you cannot predict the next one, and that is why this comes in a category of software based random number generators. Now, why do we have -1 here? Why do we always have 1 less? Is if the shift register had an initial value of 0, then no matter what operation that you perform on it, it will always remain 0. So, we have to exclude that from the number of combinations that are available, and that is why it is always 2 raised to power n minus 1. So, this is what you get. Now, the question is, how do you get the seed value? If you write a program in which you define the shift register and the taps, your problem will be how do you initialize this shift register. If you always initialize it with a known value, because in a program you say seed is equal to so on and so forth, it will always you will always predict the can always predict the sequence. So, getting the first seed value is a tricky proposition, but there are many options. If you have a microcontroller such as MSP430 and it has analog input, if you put a large enough resistor, or even if you keep the analog input open and if you sample this signal, you will find that it reads a random number or it reads a value which you cannot predict, and this could act as a seed. So, what we have done is we have used this mechanism to illustrate some a couple of code examples. In the first code example, we are going to have connect a switch on our MSP430 lunchbox on P1.3. We have also connected displays as we have seen in our previous examples in the 4-bit mode, and we have connected a very large value resistors 1 mega ohm resistor to ground. What we do that when you run this program, every time when you initialize it, when the program starts running for the first time, it will sample the analog input, use this value as the seed, initialize the LFSR with this seed, and then every time you press the switch, it will generate the next number, and you can find out what those numbers are. This is the code example. I am not going to go through it. It is by this time you would be able to very easily understand how it works. Here is the seed part initialization, and now you are trying to count numbers and print them. Now, what you will see is when you press the switch first time, it will when you turn it on, you will get a seed value, and now when you press the switch, it will feed this seed value into the LFSR, which is a 8-bit LFSR, and will produce the next number. So, every time you press a switch, you will get a new number and try to play with it to see whether you can predict the next number. We have a new modification where we modify the shift register LFSR to a 32-bit size, and instead of using a switch, we just constantly update it the value, that is shift the numbers, and the least significant bit we send it to the onboard LED of the lunchbox. What would you expect? You would expect that the LED will be on and off, but whether it is on or off or for how much time it is on or off will be pretty random. So, what you would notice is that the LED appears to flicker. So, this would be a good way to create a candle like performance on a LED, it would appear like a flickering candle. So, if you compile and download this second code example you run it, you would see that the LED which is connected to port 1.7 is flickering at a random rate and it would appear like a candle. The second part of this lecture deals with the mechanism or the requirement of converting digital numbers into analog voltages. We have already seen this in a previous lecture using the pulse width modulation technique. But the problem with pulse width modulation technique is that it is not able to produce analog voltages at a very fast rate. Why? Because of the limitation of the frequency of the PWM signal itself. And so, we are going to look at various other options of generating analog voltage using a D to A converter, and there are many mechanisms to do that. The block diagram is that you have certain number of pins here, n bits. So, you would be able to generate 2 raised to power n voltages in the range of 0 to some maximum voltage. There are various methods. The first method we have already seen using a PWM. Then you can have DAC made out of resistors and current sources and switch capacitor and resistor using R2R ladder as well as successive approximation type of DAC. In this example here we are going to create a R2R ladder network. It is called R2R because it only uses 2 values of resistor of R and a 2R. For example, you could choose R to be 10 kilo ohm and a 20 kilo ohm. So, you could choose these 2 value of resistors and connect them in this fashion. This is the R2R ladder network and it is a 8 bit DAC because we have 8 output pins from the microcontroller feeding this DAC, and here is the output, and this is the equation that governs the bit values and its impact on the actual output. When you run this code, it is going to generate a sawtooth waveform on your output pin, which is the output pin here after you. Now, it is very important that the value of these resistors are all equal, 10 kilo ohms and 20 kilo ohms. But how do you ensure that you get accurate 10 kilo ohm resistors? What you can do is you can have a bunch of resistors and then you can, using a multimeter, find out few resistors 10 kilo ohms and few 20 kilo ohms which match each other's values as much as possible, and then use that to create such a DAC. When you run this program here, I have shown that you connect port 1 pins to R2R ladder network, and when you connect it to the oscilloscope, here is what you would get as a 8 bit DAC, and this frequency is very low, but that is because the number of bits are large, 8 bits, and the frequency is not very high. And also you will see that this sawtooth is not really a straight line, and that is because the resistors are not really matched values. So, if you have better values of resistors which match each other well, then you would find that the DAC output in this case is much linear. And the reason why the frequency appears to be very low is also because a certain amount of delay has been introduced in this code. If you remove this delay, you would find that the sawtooth waveform is of a much higher frequency. Now, instead of a 8 bit DAC, you can have a 4 bit DAC, and now you see the frequency has improved, also because the number of steps that you have, instead of 256 steps, you have only 16 steps. The third part of this lecture is about revisiting the lemon battery that we created in the past. As you remember, I showed you this demonstration that we created a battery out of lemon and 2 dissimilar metals as electrodes. One was the copper here, this is copper, and what is inserted in the lemon is a different metal actually extracted out of a alkaline battery. And using this combination, each of these, so these are 4 cells, each of these cells produces 0.9 volts. So, roughly from this battery you get about 3.6 volts, and using a setup which was like this, that this is the lemon battery 1, 2, 3 and 4. We connected it to a microcontroller MSP430. Remember, we programmed it in the lunchbox, then we took the IC out, put it in the breadboard and connected the crystal to the crystal pins, so that it is working at 32 kilohertz, and then on the P1.7 pin we connected the LED like this, and the microcontroller, this is the VCC and this is the VCC pin, this is the VSS, that is the ground pin, and of course a crystal was connected to appropriate pins of the microcontroller, and you notice that this pin, this LED would blink every second in a flash. And so, I am going to go through the code and also talk about the current that this entire setup consumed. We monitored this battery over a period of 14 days, that is, this battery continued to work non-stop for 14 days. We measured the current that was being consumed by the setup, I will tell you how, and then we estimated what was the capacity of this battery. Now, when the battery battery typically has a very large output impedance, which means if you try to draw large current, the voltage will drop. And so, to make sure that the microcontroller is not affected, when the LED is turned on, it would take more current. So, we connected a large capacitor for measurement, about 4700 microfarad, so that it would filter out whenever the LED is being turned on. And we noticed the setup, let me show you the setup. What we did was, we took the battery here and connected it to the microcontroller VCC and had a small resistor connected here. This is the ground pin of the MSP430, and we connected a very large value of capacitor across this. And then we used this was about a 100 ohm resistor, and we observed the voltage on this, and from this we estimated, and of course you had the LED connected here, and from here we estimated the amount of current being consumed by this. The average current, when the LED was on, it would consume about 500 microamperes of current. When the LED was not on, it would be less, but the average current was roughly 300 microamperes. So, 300 microamperes into 14 days into 24 hours into 60 minutes will give you roughly 100 mAh battery capacity. So, this is the kind of performance you can expect out of a simple battery that you can create on your own. This is the code. You can compile and download this code. Here is the main program. The watchdog timer has been turned off. The code was using the crystal oscillator, and so it has to be ensured that the oscillator is working. So, the oscillator bit was monitored. If the oscillator flag shows a fault, you are going to wait for it, and after that you turn the timer on to give you 1 second interrupt. You turn the pins so that you are making the port P1.7 as output, and then you turn the microcontroller to operate in the low power mode 3 with the interrupt enable turned on. And so, every time the timer expired, it would take you to the interrupt vector, which is here. In that, the bit was made high. for a little while and then made low, and then you would go back into low power mode, and that was the reason why the microcontroller consumed very little power for its operation. The only time it consumed more power was when the LED was on. So, I recommend that you build this code, and if you want you can create such a battery at your own place and see how MSP430 microcontroller operates in such a low power situation by turning everything off except the time when the interrupt is generated and the LED is turned on. So, this is to highlight the low power operation of MSP430, and with this we cover how MSP430 can be used to generate random numbers, how MSP430 can be used to generate analog voltages, and also how MSP430 has this rich low power modes of operation, and you could optimize your system so that it conserves as much power as possible. I am going to stop this lecture here, and I will see you soon with a new topic. Thank you.